University of Alabama in Huntsville. First light, astrophysics from the moon.
Okay, so I am pleased to announce the first high-energy astrophysical source detected from the moon, and also the first astrophysical methodology that makes use of the lunar environment, or is uniquely enabled by the lunar environment. So, like a lot of scientific endeavors, this work was motivated by impatience and disappointment. Primarily, this plot right here. This is an all-sky map in galactic coordinates of the nuclear energy regime, the MEV regime, which was last surveyed over a decade ago. And in fact, this is a very important regime for understanding the life cycle of matter and energy in the galaxy and throughout the cosmos. We know a lot more about the cosmos at lower energies, where there are hundreds of thousands of cosmic sources detected, and at higher energies, where there are approaching 10,000 sources detected. In this middle energy range, the nuclear regime is really a dearth of sources, and we detected only 36 sources with the Compton Gamma Ray Observatory, the COMPTEL instrument on GRO. And so this is not very satisfying to me, and that's what motivated me to think a little bit outside the box. So now, why hasn't there been a sensitive sky survey or capability in this nuclear energy regime for almost 20 years? Well, it has to do with technology and money, of course. In this nuclear energy regime, which is a very difficult regime to operate in, there are technical limitations. Need a lot of mass. The techniques generally range from using coated aperture imagers at hard X-ray energies, where a heavy mask of lead with a particular pattern of holes is used to cast an X-ray shadow on a position-sensitive detector. That's a lot of mass for the next generation instruments to launch. Mass is money, and of course, tens of thousands of electronics channels is a challenge. At higher energies, at MEV energies, the real nuclear regime we want to get at, the standard approach is to use Compton scattering. But for the next generation instruments, that sets very extreme performance requirements that requires kinematic reconstruction of gamma ray interactions, hundreds of thousands of electronics channels. And this is the next generation instrument is about $1 billion, which means it's never going to fly. This is COMPTEL, the last instrument that surveyed this regime. So these techniques work, but they are really not the way to go to get that next generation sensitive sky survey. So I don't know if this will work because I converted to PowerPoint, but here's the concept of the lunar occultation technique, leveraging the unique lunar environment to do nuclear astrophysics. If you have, let's do one more click and see if this works. If you have an orbiting spacecraft around a planetary body, in this case the moon, relative to the location, to the detector itself in lunar orbit, a cosmic source will be seen to rise over the limb of the moon and set over the limb of the moon at different points in its orbit. The count rate in your light bucket will increase when the source becomes visible and decrease when the source is eclipsed. Now, this is only a cartoon version, but it shows you the basic idea. All the information about the location of the source, its intensity, and its energy spectrum is contained in these rising and setting features, the occultation features. So here, let me describe that a little bit further. The pattern of rising edges for a source and setting edges for a source for a detector in orbit around the moon is unique. It is unique because it depends on the relative orientation of the spacecraft, the moon, and the cosmic location on the sky. So every position in the cosmos will have a unique pattern of rising and setting edges that we can use to do astronomy. Every position here where the source is rising or falling, we know where our spacecraft is, we know where the moon is, and so we know the location of the limb of the moon when that event occurred. And that's going to be important in just a minute. But the key thing is that this pattern of occultation features is unique. So let's look at some data. That's all works on paper. Let's see how this operates. So I mentioned to you that this time series, this is time, orbital location, if you will. This is the occultation template for a particular location on the sky, rising and setting edges. This is actual data, which I'm going to tell you about in just a second. Life is more complicated than simulation. Why is it more complicated? You have statistical fluctuations. You also have multiple sources on the sky. You also have backgrounds. The moon is a very strong source of a gamma ray albedo. So that is unassociated with occultations, but certainly exists and will be detected by any MEV spectrometer in lunar orbit. You have cosmic and other galactic emissions, diffuse emissions, and you have unocculted sources that will be contributing to your time series data. So this is the data. We can pick out the individual occultation events, and using a robust statistical methodology, which I'm not going to bore you with here, we can actually look to see if the characteristic occultation features exist in the time series and characterize how likely that source is to be present, or is it background only. So this is great. We can write down the equations, but let's see if this actually works in principle. We want to make sure, validate this technique. So we do that as follows. There's been 6 gamma ray spectrometers that have been sent to the moon on Apollo 15 and 16, but they were only in orbit for roughly a week, so that we're not going to use those. The Chang-E 1 and 2 were fairly modest gamma ray spectrometers, so we don't have access to that data. Kaguya was a high spectral resolution gamma ray spectrometer, but that data is not public yet. It is soon to be public, I hope. And that leaves us with Lunar Prospector, which orbited the moon in the late 90s for about 1.5 years. It took 512 channel gamma ray spectra in the MEV regime every 32 seconds, and we ended up with about 130 million individual spectra over that 1.5 year period. This is the Lunar Prospector gamma ray spectrometer. It consists of a inorganic scintillator, BGO, surrounded by plastic. And I'm showing you this on purpose. It is asymmetric, which will be important in just a moment. The Lunar Prospector data sets were divided into three pieces, which are dictated primarily by their altitude differences, and also this was a spin-stabilized spacecraft. Sometimes the spin axis was pointed to the north ecliptic, and sometimes it was pointed to the south ecliptic. Our goal here is to use this data set for this relatively small gamma ray spectrometer, about 50 square centimeters, and look at the detection paradigm, all sky monitoring, localization, and see if we can see sources. So I showed you that time history, the red on and off of sources. We know the lunar limb at any of those positions, and it's unique to every location. With a very relatively small gamma ray spectrometer, we need a fairly bright source. This is, if I take that time history of rising and setting occultation features for the location of Cygnus X1, which is an X-ray binary, and in fact was the first black hole candidate identified. If I plot those occultation features onto the celestial sphere, actually, if I change the contrast here, you would see the limbs of the moon all passing through that location there. The locus of all of those limbs projected on, lunar limbs projected on the celestial sphere, is the location of the source. Now, this is just from the template. This is for a perfect world, no statistical fluctuation. It is the only source in the heavens, etc. This is the actual data from Lunar Prospector, which was not intended to do this. It was intended to do orbital geochemistry of the moon. And we find that we do in fact detect Cygnus X1 right at the location it's supposed to be. It is a statistically significant 5.5 sigma detection. um, with a localization that's consistent with our expected localization for this low statistics measure. So Cygnus X1 is actually the first high-energy astrophysical source detected from the moon, and a validation of this technique. We also looked to study if we could detect variability. Cygnus X1 is known to be variable. We only detected Cygnus X1 during a fraction of the Lunar Prospector mission, and that's because in this early part of the mission, the asymmetry of the Lunar Prospector gamma ray spectrometer, more mass was in front of the crystal, and that reduced our sensitivity, so we actually didn't detect Cygnus X1. But this is a validation that's consistent with the geometry of the detector. And just as a comparison, you can see two other instruments operating at lower energies see this variability. The error bars are large here, there's no doubt. This is a very small detector. But this leads, the whole purpose of doing this was not to just play around with Lunar Prospector, but a proof of principle of the next generation gamma ray mission. And we are going to be competing with Jack for MEDEX class mission concept, friendly competition, to do nuclear time domain astronomy. We have a pretty dynamic collaboration, and we're tackling a number of questions that were part of the decadal review related to nuclear astrophysics and time domain astronomy. In particular, our primary focus, the driver of this mission, is detailed studies of type 1a supernovae, which are critical for doing precision cosmology and measures of dark energy. There's actually a lot of mystery about these objects, including what their progenitors are. I'm going to run out of time, but by looking at the gamma ray emission from hundreds, if not thousands, of these type 1a supernovae, we can start to discriminate between different progenitor models, measure the mass dispersion of those progenitors, characterize subclasses of type 1a supernova, measure the local supernova rate, which is actually unknown to factors of 2 or 3, and is critical for understanding nucleosynthesis, and also probe standard candle systematics that ultimately go to our understanding of cosmology and dark energy. And I'll say that these measurements are directly coupled with the two highest ranked space and ground-based endeavors, the W-FIRST mission, which is NASA's highest ranked mission, and the Large Synaptic Survey Telescope, which is NSF's highest ranked astrophysics effort. And I'll just end with this. This is true for any of us that are trying to do astrophysics on the moon. Science fiction. It's often believed that the first science fiction novel, which was actually written by Johannes Kepler, yes, that Kepler, that science fiction novel called Somnium actually was about doing moon-based astronomy, believe it or not, the first science fiction novel. And whether it's Dare or Locks or something else, probably Locks, but I don't know, we'll see. We're turning science fiction into science fact, and both of these endeavors are really using the unique and special, leveraging that special lunar environment to do astrophysics that is really unattainable on a terrestrial platform. Thanks.
Are there any questions for our speaker? I see one question. Please identify yourself.
Jim Christian, thank you. That's a very nice talk. I just wanted to ask a question about whether the geometry of the scintillation detector, if it's more asymmetric, is that better or worse for these occultation measurements? And sort of a related question is, after you look at your data, is there any sort of higher level image processing that you can imagine doing to try to sort of, it looks to me like a little bit of a Compton where you're overlapping arcs, and you say, well, is there higher order image processing that you might be able to?
Those are both good questions. So the answer to the first question is it depends what you're trying to do. If our primary goal is supernova, you never know where a supernova is going to go off at any time. And so we want to do continuous all-sky monitoring. And so we want as uniform sky coverage as possible. If we were trying to do targeted observations, then an asymmetric scintillator array would be good because then that helps with position sensitivity. What I didn't say, I have a poster, but it's the end of the day, so probably won't get looked at, is this technique actually does phenomenal with position sensitivity at about 5 arc minutes, whereas competing techniques are about 1 degree. So position sensitivity is less important than all sky coverage uniformity. Sorry, I forget what your second question was.
Processing.
Oh, the processing. We actually don't do the imaging you saw. The maps are just graphical representations. The actual analysis doesn't make use of the overlapping arcs. It's actually done on a statistic. It isn't done that way. I can talk to you about it afterwards. That's really just for graphical, for communication purposes.
Thank you very much.